By the time I discovered the class was over. So um, I feel sad that I have to repeat everything I said. I think I was talking to myself without knowing, but I'll repeat it to the best of my ability. I'll try and repeat some of the things I think I said. Perhaps I'll just go a little bit faster than I would have wanted to. So if I go very fast and you don't understand, please just stop me. I try to ask where I got lost. So I will try to repeat from where I was told I left. Mhm. So if I get disconnected, if by chance I get disconnected and I don't know, please someone should call me. I think the class reps have my number. Please, you call me. Last time what happened is that my phone was also off. So I think there are people who tried to call me. I did not know my phone was off, but today it's on. So if anything happens, just let me know by calling. So I hope you can see what I'm projecting.
Yes.
I was told that I got lost around here, buffer allocation. I talked about packet reordering and round trip time and how they affect the sliding window. Is that correct?
Yes, it's correct.
Right. So I'll try to put it in context. What you were talking about was we were trying to understand the operating environment of the sliding window. In what kind of environment? Oh, yeah, the data transfer phase and the operating environment of the data transfer phase. So we said there were, it uses the sliding window, but needs to change some things about the sliding window because of the environment that transport layer is operating on. Now, concerning the buffer allocation, I think I said that buffer allocation in the case where you have two directly connected nodes, you know the capacity of the link. In other words, you know how fast data can be transferred on that link. And you know how fast the receiver can process the data. And so it's possible to have a buffer that can accommodate the rate at which data is coming in. And so we tend to have a fixed buffer size, and we tend to have a fixed window size in where they are directly connected. But I say that with the TCP connection, having a fixed window size does not work because you talked about the round trip delay. Having a fixed window size, having a fixed buffer size, it's not possible because of the dynamic nature of things at the transport layer. And so, what happens is that the buffer allocation on the receiver side is not constant. I think I tried to explain why, but I think I left out something very important, which I will add to that. So assume this is the receiver. That is the receiver. Assume that's the transport layer. And this is the application running on top of the transport layer. Inside the transport layer, we know there are buffers. There's a receive buffer. If it's only receiving, if data is going in one direction. But if it's also sending, it will also have a send buffer. But let's just assume it's only receiving. When data comes in, it is stored in memory. And this is the part I think I didn't mention last time. The application that's running on top must pull the data by using the read request. When it says it wants to read, it tells the transport layer it wants to read. It's like it's pulling the data from this buffer. So when it issues a read request, it pulls one of the messages. And then when it wants to read the next one, it pulls it. So whatever it pulls out of that buffer is removed by the transport layer and given to the application. Now, if the application does not pull the data will remain in that buffer. So if the sender keeps sending more data, then we have a problem. Because this sender also has a send buffer, which is inside the transport layer of this side. And the application is running on top of here. So when this application has something to send, it uses the send primitive. It uses the send request, and therefore it pushes data into this buffer, which is within the transport layer. So if this sender keeps sending data and the application that is supposed to pull the data is not pulling it, then it means this buffer will get full. At some point it will get full, and therefore this side needs to tell the sender that it has run out of buffer space. And so what I'm just basically saying is that the buffer space that is available, it's not static. Because, for example, if the buffer space on the receiver side were 8 spaces or a buffer of 8 messages, and this side has sent 4 messages, and the receiver has not pulled any, then the buffer size remains 4. It now becomes 4. It was originally 8, it has received 4, and the receiver has not pulled it. So this side only has a buffer space of 4 to send 4 more messages. If it sends those 4 messages and the buffer becomes full, then there is no more buffer space to send more. So basically this buffer space that's available on this side is dynamic. It's not constant. And this side has to know how much buffer space do I still have to send more data. But remember, I also told you that connections are created and terminated. At any one time, connections are not static, and the buffer space has to be reorganized to accommodate the connections that are there. So generally, buffer space in a TCP environment is not a constant value. So whereas the normal sliding window operates from a perspective that the buffer space is on the receiving side is constant, this one cannot operate that way. And another thing I need to say is that whereas this data has been received and is in the buffer and it has not been pulled, remember that the receiver will send an acknowledgement. It will send an acknowledgement. and say, I have received 3 messages or 4 messages. In the normal sliding window, an acknowledgement would mean that you can send more data. In the TCP, an acknowledgement just means I have received the data. It doesn't mean it has been passed to the upper layer, because in the normal sliding window, you send an acknowledgement when you have processed the data and you have passed it to the upper layer. So when you get an acknowledgement, it means you can send. That's really what it means. If one of them is acknowledged, you can open the window and send another one. But in the transport layer, it's not the same thing. You send an acknowledgement just to mean I have received it, not that I have passed it to the upper layer. So if the sender believes that you have sent an acknowledgement and now there is more buffer space, that assumption will be wrong, because the receiving application may not have pulled the data up. So yes, the data has arrived, it is in the buffer, but there is no space to send another one until the client pulls it. So whereas in the lower layers, whenever a layer receives data, it passes it to the upper layer. When it comes to the transport layer, you cannot force the application. You cannot give the application data by force. You let it request for it. So that's where the difference comes. So therefore, buffer space is not a constant, and receiving an acknowledgement does not mean you can send anymore. So typically what happens, how then does the sender know how much buffer space is still available? Yes, the 4 messages it sent have been acknowledged. But how much buffer space is left? It doesn't know. So normally that message has to come from the receiver. The receiver acknowledges and also tells the receiver or the sender how much buffer space is left so that it can send more data. So that's one of the issues that the transport layer has to deal with, that in the normal scenario, they don't deal with it. Now, the other issue is network congestion. Now, network congestion arises at the transport layer. It doesn't arise at the data link layer. In this sense, when you have 2 devices that are directly connected, as we have said, you know the capacity of the link. You know the capacity of the link between these 2 devices. So let's assume it is 10 megabits per second link. So you know the receiver basically knows how fast the data will be transmitted to it. So it knows that every second it can receive 10 million bits. And the sender, how do I put it? Let me try and draw it in a different way, because I want to distinguish what happens from in the transport layer with what happens in the data link layer. So let me redraw
Option
this diagram.
is we can look at it in 2 ways. We can look at it generally.
The bottom here.
So
So assume these are the intermediate nodes between source and destination. Between source and destination, those are intermediate nodes. The receiving node is here, so that's the recipient. and the sender is on this other side. So I wanted to say that when you have two directly connected nodes, as we have here, because data link layer operates between these two nodes. So assume you have two nodes that are directly connected. You know the capacity of the link. So when the sender sends, they know, the receiver knows the rate at which it will receive the data because they share the same link and they know how fast that link can transmit. So in a point-to-point link, ideally, one end cannot send data faster than the receiver can receive it, or faster than the link allows. Let's put it that way. So if it's a 10 megabits per second link, you cannot send faster than 10 megabits per second.
Examples of algorithms in NP.
It's not possible.
That is the consecutive travel assessment.
Now, when you're operating in a wide area environment, remember you have several intermediate links. And these links are not of the same capacity because these links may belong in different jurisdictions. Let's put it that way. So let's assume that this link, or even let's just assume they are all 10 megabits per second links, these ones. They are 10 megabits per second link. But the rate at which data is arriving on, the rate at which data is being transmitted on this link is maybe 1,000 frames per second, let's assume. Let me just use that as an example. So between these two nodes, data is being sent at 1,000 frames per second. On this other link, data is being sent at 10,000 frames per second. Now, that means that there will be a buffer here to receive those frames that are coming in at 1,000 frames per second, right? And let's just assume that this link here is faster than this one. So maybe here the data is flowing at 1,000 frames per second. But at this link, let me redo that. On this side, the data is flowing at 500 frames per second. So data is coming in at 1,000 frames per second, but it can only go out at 500 frames per second. Then it means that you begin to have a queue buildup. A queue will begin to build up here because 1,000 per second, only 500 can be sent because this link is not of the same speed as the previous one. And there are two links, but they have two different speeds, which is what can happen when you have a TCP connection. You do not know the route which your data is going to pass through. You do not know which links are going to be used. You do not know the capacity of the links that are going to be used. So you may not know what will happen in the network. But assume that this user here has the capacity to send data at 1,000 frames per second. And that's just an assumption. And there's another node connected here. There's another user node connected here. I can't draw it because of space, but it's also pouring in data in here at 1,000 frames per second. Okay, so the users are sending into the network, and we shall say that this network, the operator of the network operates here. So the users don't really know what's going on in the network. They have just been given a connection to connect to the network. So with that connection, they can send data into the network. So these two devices are sending data to their initial node, initial router, both of them at 1,000 packets or frames per second. Now, as I said earlier, on this link, you can only send 1,000 frames per second. But notice that on this link, we are having 2,000 frames coming per second. So again, on this node, you begin to have a queue buildup. The queue that sends data out on this link will begin to build up because it's receiving 2,000 every second, but it's only able to transmit on this link at 1,000 frames per second. On this node, it's coming in at 1,000 per second, but it's going out at 500 frames per second. So again, we said, you can think about it that a queue will also begin to build up here. And so on and so forth. Depending on the characteristics of the network, you may find that this node here also has several computers connected to it or networks, and maybe data is coming into the network through this node at different rates. So let me just exaggerate here. Let's assume this one is also coming in at 1,000, and this one is coming in at 1,000, and this one is coming in here at 500, right? But this outgoing link maybe can only send 1,500. Notice it's receiving 2,500 per second, but can only send 1,500. So really, it will begin to build a queue of packets within it. So congestion begins in that way. And how exactly does it begin to do that way? Because the senders of data into the network do not know, they are not aware of what all the other senders are doing. They just see the link into the network and they use it to send data. But they may not know that within the network, there are some slower links. So this one is 1,000, the other one is 1,000, but this is 500. And they don't know that when it reaches that 500 frames per second link, things now will have to slow down. So users are sending data into the network at their own rate based on their link. But the combined force of the data that is sent into the network may be more than the capacity which the network itself can service. So at that point, queues begin to build up within the network, and data begins to take long within the network. Now, the minute those queues build up and fill, then the nodes begin, the intermediate nodes begin to drop data. And now we've entered a stage we call network congestion. The minute that routers begin to drop packets, we have begun to have congestion. Now, what happens with congestion is that packets take a long time to reach where they're going. So I just feel like I'm not having enough space to explain what I want, but maybe I should use another diagram. Maybe let me try with this one. So as I've said already, if there's a sender sending here, and maybe the destination is here, and based on who else is sending in the network, we say that at each node, there are queues. And these queues may begin to build up. If data is going in that route, queues may begin to build up because there's a difference between what is coming in and what is going out. So queues will begin to build. So these nodes are all sending. They are all pushing their data into the network. These are transmitting nodes. So depending on the rate at which they are pushing data, you find that sometimes the routers get data at a speed at which they cannot be able to service. So if we take the example we gave, or I gave earlier, data is coming in here at 1,000 frames per second. I said that this node here is also sending data at 1,000 frames per second. And let's just assume for simplicity that the route chosen for it is this one. So data may come in here also at 1000 frames per second. It's coming in from node A at 1000 frames per second. But this route here can only send 1000 frames per second. So this queue is building up here. This one is building up. And remember, I said every second it's sending 1000 frames. So with every second, the queue is building up by 1000 frames. So after 5 seconds, you will have 5000 frames in the queue.
Now it's the
Okay,
customer that has
so that you have to know that these nodes keep on sending. So they send the first second 1000, the second 1000, and so on and so forth, and this one also. But at any one time, only part of it is going out. So this queue is building up, and the more they send, the more the queue builds up. Now, if data comes in here at 1000 frames per second, and this one is sending at 1000 frames per second, this one is sending at 1000 frames per second, but this line here is only able to transmit at 500 frames per second. Now you realize that the queue that is going out here, the queue for this line, this second line, I can't find my pen, but this second line here, the queue, the outgoing queue for that line is also building up. So every second, it's receiving 3000 frames, but only sending 500. So every second, it's having a backlog of 2500. The next second, it will have another backlog of 2500. And the next one, another backlog of 2500. So you can imagine the queue is building up in node 2. Now, again, if you assume the same thing is happening in node 3, this is coming in at 1000 frames per second. And I just want to exaggerate it so that I explain what congestion is. So these two are putting data into the network at 1000 frames per second. It's coming in here at 500. So in total, we have 2500. And let me assume that this is going out at 1000 frames per second. So it's receiving 2500 every second, but going out at 1000. So it has a backlog of 1500 and so on. So the queues begin to build up. So if a frame is going from node A going to node B, notice that it enters this queue here, and it finds already there are so many frames in the queue, so it goes to the back of the queue, and it makes its way slowly to the front of the queue before it is pushed out here. And when it enters here, of course, it will be processed and put on the queue for going out there. Again, it may enter that queue at the back of at the bottom of the queue, or at the end of the queue, and then it makes its way slowly to the front of the queue. And when it comes here, it may also do the same thing. And remember, every second the queue is becoming longer. So that means every second it's becoming, there's a greater delay in terms of the data making its way from node A to node B. Notice that our node B is here on node 6. That's our node B. So it's becoming, the delay between A and B is increasing with time. Okay? Now, as I said, the point where now congestion begins to come in is when now those queues begin to fill up. So that when a message is sent from A to node 1, maybe let's assume that node is not full. But maybe when it gets to node 2, it finds that that outgoing link that is sending at 500 is now full. So what will happen? It will be dropped. It will never get to B. What will node A do? Node A will retransmit. Now it's retransmitting into an already full network, an already congested network. So what will be the probability of the message making it to B, it's not a probability of 1, definitely. It may make its way to node 2, it may even make its way to node 3, but it may find that maybe the queue at node 3 is full, it will be dropped again. A is waiting for an acknowledgement, it's not getting it, it retransmits the same frame, it retransmits it again. And it may have to retransmit it several times. Now, I'm only using A as an example. But remember that all these nodes that I have drawn there, they are also transmitting into a busy network. And the probability of their packets getting to the destination is becoming lower and lower with time. So they also begin to retransmit. And now you realize that for every packet that has been transmitted, maybe there are 3 more duplicates of the same packet, because that's congestion builds upon itself. It causes the nodes to retransmit, they retransmit, and the packets are getting dropped or they're taking long. So you may have duplicates of the packet within the network trying to make their way to their destination, but they're stuck in the queues along the way. Okay, so now congestion is really building up. If you think that the original packets are stuck in the queues, the duplicates are also stuck in the queues, and some of them are getting dropped, forcing the transmitters to retransmit them, the transmitters to retransmit them. So the queues are getting longer, the network is becoming more and more congested. And what happens with congestion is that it reaches a point when the probability of data making it from A to B actually drops to, let's just say 0. It just drops to 0. In other words, the network is not pushing anything out. Data is coming in, but because of the congestion and the queues that are filling up with time and becoming longer and longer with time and dropping packets, the probability, the network grinds to a halt, in other words. It just grinds to a halt. In other words, you cannot move data from point A to point B. And now you have a congested network. Congestion has now reached its limit. Now you can try and compare this with what happens on our roads when we have a jam. You know, jam begins to build slowly, but it reaches a point when the jam is just too much. Of course, unless the policemen are on the road. If they're on the road, they probably do something and cars will begin to move. But if it's just the normal human beings without the help of police, sometimes you find the network just, or the road network just grinds to a halt and cars are not moving. Yeah, I don't know if you've ever seen that situation, but it can happen. With time, no one is moving. So we are all stuck in the jam. And so the same thing happens in the network, and we call that thing network congestion. That's really all I want to say. Now, so in the context of data transfer, because that's where we are talking about how we transfer data between source and destination. Obviously, we'll have to find the equivalent of the police to try and remove the deadlock in the jam. So the transport layer also has what we call network congestion control protocols, which should try to ensure that if there's a network congestion, we deal with it so that obviously data transmission can proceed, because there's no point of having a network and nothing is getting to its destination. So we have what we call transport layer congestion control techniques, something we won't go into in this topic, but it's just good to know. But it's also good to know that congestion control can also be done at the network layer, because these intermediate nodes, they are part of the network layer. We said that the transport layer only operates on node A and node B, but they can still do congestion control. How? By telling the sender to stop sending. So for example, in the case of A sending to node 1, if node 1 is receiving packets from A and those packets are getting dropped, then ideally node 1 should tell computer A to stop sending. Now that is actually being done at the network layer. So the routers can send back information to the source of the packet to tell them to stop sending, to stop putting more data into the network because the network is congested. So that would be network congestion control at the network layer. But also the transport layer has its own network congestion control mechanisms where the receiving transport layer can send back data to the sending network, to the sending transport layer to tell it to stop putting more data into the network. And therefore it eases the jam, because the problem here is the queues. Data is entering into the queues and taking too long to come out. So if A, B, C, all those computers are grown on the network, if they are told to stop pouring more data into the network, then obviously with time, the congestion will sort itself out, and then they can be given the freedom now to send more data into the network. But obviously you realize that network congestion will interfere with data transfer. So you can create a connection, enter the data transfer phase. If there's network congestion, you will not communicate. So these network transport layer congestion control techniques must kick in for that connection to be functional. I hope I have tried to describe congestion. As I said, ideally, you should have done network congestion control at the network layer. I don't think we had time for that. Transport layer congestion control, neither will we have time for that. But what I have said can get you started. You can read more about network congestion and control techniques at the network layer, and network congestion and transport layer congestion control techniques. All those things are in the textbooks that I've given you. Now, finally, let me, now if you read this, it will just be trying to describe this diagram here, which basically tries to say that each of these intermediate nodes has a queue. And when data comes in, it enters the input queue, and then the data is transferred to its output queue. So here, not all the queues are shown. But if you look at node 5, for example, let me just use node 5 as an example. Data coming from node 4 to node 5 will enter the input queue of node 5 on that link. So every link has its own queues. So the link from node 4 to 5 has an input queue. It is drawn there next to node 5. So any data coming from node 4 will go into that input queue. So node 5, assuming the data is to be sent to node 6, node 5 will pull the data from the input queue, process it, and determine that it is to be sent to node 6. Then it will put it on the output queue for node 5 on that particular link 5 to 6. So if you see those two, these two queues, this is the output queue and this is the input queue for these links here, this link here and this one. Now, remember that if data is coming from node 6 this way, there also needs to be an input queue here for this link. And if data is going out here, there will be an output queue for this link. Okay, so on every link there's an input queue and an output queue. And of course, on node 5, if you look at this line here, there'll also be an input queue and there'll be an output queue. So that when data gets to a node, it's first put in the input queue, it is then processed, then it is put in the output queue for the corresponding line it is supposed to go out through, and then it is transmitted. Now, of course, if the network is congested, as we've said, then a packet takes quite a while in the input queue and in the output queue. So it takes a long time to go through any particular node. The more congested the network is, the longer the delay to pass through any node. And there's a possibility that it could even be dropped. Okay? So let me conclude. So that's what this part is saying. So let me conclude by talking about these delays. So if you've understood the queues I've talked about, network congestion, as we said, makes it impossible for data to make its way to its destination. The delay is too long for it to make its way to the destination. But you need to take into account that these delays are part of what makes it difficult for a packet to reach its destination. There's what we call the processing delay. Now, it is the delay between the time of reception of a packet. Remember, it comes into the input queue. So the time of reception of a packet in the receive queue, or what I've called the input queue, to the point of putting it into the transmission queue or the output queue, after it has been processed. So when you're talking about processing delay, you're actually talking about the fact that it has spent some time in the input queue, it has been processed, and then it has been put in the output queue. Whatever that delay is, that's what we call the processing delay. Now, the queuing delay, this is the delay between the point of entry of a packet in the output queue, the transmit queue. So the processing delay has removed it from the input queue, has processed it, and put it in the output queue. So it's now waiting to make its way to the top of the queue to be sent out. Now, the time it takes in that queue is what we call the queuing delay. Now, what is the transmission delay? The transmission delay assumes it has reached the top of the output queue, and now it needs to be transmitted. So transmission delay is the time it takes to transmit it on a given line. So if the line is transmitting at 10 megabits per second and the frame is maybe 1000 bits, you can always work out how much time it will take to transmit it. That's the transmission delay. Then the propagation delay is the time it takes for it to move from one node to the other. So you can imagine if data is making its way through the network, at each node, it will experience the processing delay, the queuing delay, the transmission delay, and the propagation delay before it reaches the next node. When it reaches, for example, node 4 from node 1, it will experience processing delay, it will experience queuing delay, transmission delay, and propagation delay before it reaches node 5. At node 5, it will experience all those delays before it reaches node 6. Now, obviously, the one that is of great interest to us when we're talking about congestion, one, of course, is the processing delay, because the processing delay includes the time it takes in the input queue. So if the input queue is long, then the processing delay will take long. Similarly, the queuing delay, once it has been put in the output queue for it to be sent out, and the queue is long, it will take a while for it to reach the top of the queue for it to be transmitted. So when we have congestion, processing delay and queuing delay are the ones that greatly contribute to how long it takes a packet to make its way from point A to point B. And the longer the queues, the longer the time. And then, as I've said, the more time it takes in the network, the more the transmitting stations panic or time out and send a second copy. So now remember, the first copy is stuck in some queue somewhere, and the transcender has sent another packet, which is also going to take its way through the network and experiencing all these delays. And maybe by the time the sender times out, this second copy is also somewhere making its way somewhere within the system, making its way to the destination. The sender times out and retransmits again. So now we have 3 copies of the same packet in the network, and they are all stuck at different stages. And if you remember when we talked about connection establishment, and we said that some packet reappears from somewhere, from some unknown place, and it interferes. Now you understand where it comes from. Most likely, maybe there was congestion, so it got stuck in the network at somewhere, and then it reappeared at a time you didn't expect it to appear, but it appears. Because if it successfully makes its way through the network, it will appear. If it is not, discarded. But if you think the fact that all those nodes will be doing the same thing, sending the first, second, third, fourth copy of the same message, now you know you have 4 times of what you should really be having in the network, with duplicates upon duplicates of packets. The more duplicates you have, the more congested the network is, and the slower the packets take to reach their destination. But ultimately, the network will come to a standstill when nothing is actually moving. That's really what will happen at the end of the day. And now you have a deadlock. Right. So those are things that happen at the transport layer and interfere with the data transmission. So unless you have a question, I want to move away from that topic. Have you followed what I've said? Does it make sense?
Yes.
Okay. Now, those same things I've talked about are in these notes here. Actually, I didn't intend for them to be here. I think I just forgot to delete them. So I'll skip them. When I come to that point, I'll just skip that part because I think I've explained the factors that interfere with transmission. Right. So now I want to talk about error control and flow control. If I can cover those 2 topics, I'll be pretty happy. Then we'll be left with one more topic. So error control, we'll cover error control and flow control. Multiplexing may take a bit of time, but I think it's another important topic. So let me just try to rush through error control and flow control. Actually not rush through, because you already know about the sliding window. So this is a modification of the sliding window. So probably I should just concentrate on where the modification is, because the basics of sliding window you know. So the transport layer uses sliding window to do error control and flow control, but it's slightly different from what you already know, for the reasons I have been trying to describe there. Okay. So in a transport connection, of course, we have to deal with the unreliability of the network, which means we'll have out of order delivery, lost messages, and duplicate segments, okay? But TCP tries to provide a reliable service with messages that are submitted in the correct order, okay? So that means that the transport layer should be able to detect corrupted messages. It should be able to detect lost messages. It should be able to recognize duplicates and things like that, so that it requests for retransmission, because it's really trying to do reliable delivery. So if any packet is lost, it should ask for a retransmission. If it is corrupted, it should ask for a retransmission. Things like that, things that you already know. Now, of course, to do this, it will need a sliding window protocol, where sliding window just means you know what data you expect, and if you don't get it, or if it comes in and it's corrupted, you know what to ask for. But you're not limited to just receiving one message. You are limited. You are limited with this, the window, the size of the window. You are limited to how much you can send before you start waiting for a response. Now, so TCP uses the sliding window protocol, and I need to highlight at this point that I think I've already said it. With TCP, the packets are numbered based on each byte has a number. Let's put it that way. Each byte that is being transmitted is given a serial number. So when in the part where the packet, in the part where the system should say what is the sequence number of a particular segment, we actually put the sequence number of the first byte in that segment. Remember, the segment may contain several bytes, but the sequence number is the sequence number of the first byte that is being sent. So let's assume that a packet or a segment is containing 200 bytes. And when the connection was being established, we were to start numbering them from 1. So the sequence number for the first packet will be 1, but it's containing 200 bytes. Now, when the receiver receives that packet, it will acknowledge. What will be the acknowledgement number? It will not be 1 plus 1, it will not be 2. The acknowledgement number will be 200. In other words, it will be trying to say, I have received 200 bytes, and now I will be expecting the next byte I'll be expecting should start, the next message I'll be expecting should start from byte number 201. So the acknowledgement number will be 201. Remember, the sequence number was 1, but it was carrying 200 bytes. The acknowledgement will be 201. Now, when it sends the second packet, the sequence number will be 201, because now the first byte in that message is the byte number 201. But it will be carrying 200 bytes. So when it reaches the receiver will receive another 200 bytes. What will the acknowledgement be? It will be 401. It will say, look, I have received up to byte number 400. So I expect to receive byte number 400, starting from byte number 400. So when it receives an acknowledgement with sequence number 401, the next message it sends will have sequence number 401. So you need to remember that it is the bytes that are numbered. So you know that each of these what do I say, letters, if I were to send a text, so each of these letters here would be numbered. Okay, if I were to send this text message, then depending on how many bytes can be in a message, each of the bytes in this text would have to be numbered. But the sequence number will be for the sequence number of the first byte. Okay, so you use the sliding window, the data is sent, and the receiving transport layer informs the sending transport layer if there are any problems. So for example, if a message got lost, or if one got corrupted, then it would have to send some acknowledgement back to the sending transport layer. So that's what this diagram is really just showing, something you already know. It will send back something to the sender to say that things are not the way you expect. So, so error control expects them to use a sequence number, as I've said, and an acknowledgement number, And the sequence number can then be used to detect duplicates. So if a message was sent that had a sequence number 201, and maybe a retransmission is done and another message with sequence number 201 is sent, then the receiver should know that this is a duplicate. So the sequence number is used to detect duplicates. Of course, we've already also talked about the wrapping around of sequence numbers, depending on the number of bits you're using to represent the sequence numbers. And the receiving transport layer, of course, will acknowledge, the acknowledgement will tell the receiver what is missing, okay, or what it has not received. So the sequence number should tell it whether or not it should retransmit or whether it should send a new message. Now, this process, I think we've basically talked about it. What does the sending transport do? Remember that a message comes in, it goes into the send buffer. There are two buffers I think I have that diagram. There are basically two buffers on each side. So let me use this diagram to remind you. I think I've actually talked about this. I've actually talked about it, but let me just repeat myself, I think, in case maybe it was not clear. So data is coming in from the application and it's going into the receive buffer. So this is the receive buffer. So when a sender, an application is sending data, whatever message it sends, the number of bytes it sends will go into each of these buffers. So maybe that will be the first message, the second message, and so on. Okay. And so that's the receive buffer or the transmit buffer. Here it's called the transmit buffer, of the buffer from which the sender will transmit. Now, when it reaches the other side, this will be the receive buffer. So they'll come in here. And as I mentioned earlier, the application will pull it when it is ready. If it is not ready to pull it, it will stay in the buffer. But this is only a one-way transmission. If this side is also transmitting, then it will also have its transmit buffer, where data will come from this application to be transmitted in this direction. And then there, of course, will be a receive buffer on this side. So at each side, there are two buffers, a transmit buffer and a receive buffer, to support the two-way communication, okay? So a transport entity receives a message from the sending process. So if the process is sending data, the transport layer will receive it together with everything it needs. Remember, there's a source port and there's the IP address and so on, that composite address. It will be passed down to the transport layer. So the transport layer will add a header, and then that particular message will now be called a segment. And then obviously it will enter the send buffer and then it will be transmitted. Now, the sender keeps information that helps it know what has been acknowledged and what has not been acknowledged. So this is what the sender will keep. Remember, there's data that it has sent and has been acknowledged. So that one is already out of the buffer. Notice it has been removed from the buffer. It already knows. So if it had sequenced its numbers, for example, from 0 to maybe from 0 to 1,000, and maybe from 0 to 100 has been received and acknowledged, then obviously that will be out of the buffer. Then it has the send window, those that have been sent and not acknowledged. Then there are those that are already in the receive buffer or the transmit buffer, but have not been sent. So it needs to keep these variables to know when to slide the window. I think that is something you already know. On the receiving side, as we've said, data comes in, it is added to the receive buffer, and then the receiver sends the acknowledgement. And I've said the acknowledgement is sent not because the data has been passed to the application, but just because it is sitting in the receive buffer. So an acknowledgement just means I have received it. It does not mean I have passed it to the application. It means I have received it and it is in my buffer. So it sends an acknowledgement, as I already said, using the acknowledgement numbers. And so the sender may send an acknowledgement for each message, or it may send an acknowledgement for several messages. Obviously, if you receive an acknowledgement for frame number 3, now I'm using the old context. If you are sending data in bytes of 200, you send the one that had sequence number 1, the one that had sequence number 201, and the one that has sequence number 401. If the sender receives one acknowledgement saying the next frame I expect to receive is 601, then that acknowledgement means it has received all the others, because it would not have acknowledged. If there's a message that has arrived out of sequence, then it has to wait until the in-sequence message comes before it acknowledges. But if you get an acknowledgement, then it means all the others before it have already been received. So it may acknowledge one by one or acknowledge them as a group. So each buffered segment is processed. And notice that it examines the header, because that's where the error detection mechanism is in there. So if there's any problem with the message, it will definitely no, that doesn't mean that. That would have happened before it acknowledged. If the message arrived with errors, it would have been processed before being put in the input buffer. This processing here basically means that it passes it to the correct application. And the reason why it needs to be processed is because on any computer, you can have multiple applications running. So it needs to process and to know which application should it pass it to, which of the running applications should receive it. Now, I've highlighted there, I think I need to relook these notes, but anyway, notice that I've put in the last bullet there, it tries to say that until the application reads the message will be stored in the buffer. So data comes in, it is acknowledged, and then it remains in the buffer until the receiver reads it or pulls it, what I'm calling pulling. Reading is the means of pulling it into the application. So the both sides should have this data. They should have some way of knowing. That is really what I was talking about here with this window. It should know what was the last byte written by the application. In other words, if the application is sending data and every byte is numbered, so which was the last byte that the application passed to the transport layer? Which was the last byte that the transport layer sent to the receiving side? Which was the last byte that the receiver acknowledged? And on the receiver side, it should know which was the last byte that the application read. what was the last byte it received, and what was the next byte it is expecting. So here, the issue of bytes is very important. So it keeps track of the data being sent based on bytes and not on the sequence numbers. The sequence number just helps it to know where to start from, where to start counting the bytes. So I want us to look at this diagram, and then I will just, so I hope you have these notes. I hope you can see what's on my screen. So I'll just use it to explain. It will be an example of how communication can take place between two sides. So please just follow with me. We'll start from the beginning, right? So we are in the data transfer phase here. So there are not those SYNs and so on. We assume they have already happened. So if you look at this first message that is being sent, notice the sequence number. It's from 501 to 600, which means that in this message, there are 100 bytes being sent. But what is really the sequence number? The sequence number should really be 501, because there's only one space for one sequence number. So even though here it's written 501 to 600, the sequence number will really be for the first byte. So that message is sent to the server, from the client to the server. Notice that the received buffer has received 100 bytes. So that message is put in the receive buffer. Now, secondly, this side also sends another message, but now it's starting from 601 to 700, which means it's carrying 100 bytes. It is also sent and it is put in the buffer. So now we have 200 bytes in the buffer. Notice the acknowledgement. The acknowledgement should say the sequence number of the next byte it expects. So since these are, how many? These are from 501 to 700. So the next sequence number of the byte it expects is 701. So the acknowledgement just carries the acknowledgement of the next byte. In other words, it's acknowledging that it has received up to byte number 700, and now the next one it expects is 701. So that arrives on the sender side. Now the sender now sends another packet. It starts from 701 to 800. Notice that it gets lost. Okay. So it still doesn't know because it's waiting for an acknowledgement. Remember, we looked at it, how the window works. We said that the window here looks at those that have been sent but not acknowledged. So it's still there. It's waiting for an acknowledgement. Now it sends another frame, but this one is starting now from 801 to 900. So it sends that, and it is received. And notice that the one that got lost, the space is reserved because it's definitely in the receive window of the server. So the server knows it should have received byte 701 to 800, even though it didn't receive it, but now it has received 801 to 900. So it has received it, and this is out of order. Notice that it is out of order. So even if the application did a read, this would never be given to the application until this one arrives. So now this one sends an acknowledgement. Which acknowledgement does it send? Notice it has received up to 900. But it must acknowledge up to what is in order, not up to what is out of order, not just up to what is in order. Now, up to what is in order, it has received up to 700. And the next one it was expecting in order is 701. So that acknowledgement is sent back to the sender. So the sender then gets to know that that frame that it sent that was starting with 701, definitely it was not received. So it has to transmit it again. So now it sends the 701 to 800, and when it arrives, it's now in order, and everything falls in order. So it sends an acknowledgement now for both of them. For both of them. So now the next byte it expects is 901. So that's how transmission takes place in terms of error control. So any questions on error control? I hope you're following with me, that diagram.
For the first send,
Yeah.
there was no acknowledgement. So does it wait for you to send two consecutive segments first, or what?
No, but you see, you forget what I already said. It's already in your notes where we said it can acknowledge one by one, or it can acknowledge, I think it was somewhere in your notes, but I said it may acknowledge one segment, or it may acknowledge a group of segments. I think I said it at some point. Yeah, so here I said it can acknowledge each packet, or it can acknowledge a collection of packets. It just depends on how things happen. It really doesn't matter as long as it acknowledges. So you're asking about the first one. Maybe it just wasn't ready to send this acknowledgement, or it was in the process when this other message arrived. So it did not see the point of sending this acknowledgement and also sending this acknowledgement, because that would have also been okay. So maybe it just happens that when this message arrived, it was in the process, or maybe it just felt that it was appropriate to send that acknowledgement. I'm not sure exactly what happened, but it depends on the speed at which it's able to process and what's already there by the time it's doing the acknowledgement. So it's free to send an acknowledgement for each packet, or to send a group. And I think this is the best example of why it needs to send as a group, because already it could not send an acknowledgement for this one because it was out of order. But immediately that this one arrived, they both fell in order. So there's no need to acknowledge each. It can just acknowledge both of them by saying which frame it is now expecting. But in short, to answer your question, you can acknowledge one by one, or you can acknowledge as a group.
Okay, so it's safe to assume that the first segment for 501 in the client, in the send but not acknowledged, let's say send but not acknowledged window, the 501 segment is still there in the client, in the transmit queue.
Oh yes, it cannot be removed until it has been acknowledged. So that if it is not acknowledged, you have it and you can retransmit it. So it must remain in the queue until it is acknowledged. Remember that you slide the window once the data has been acknowledged. You slide the window and you remove the data from the buffer. Yeah, so you are right in that sense.
Is there a mechanism to automatically remove such segments that have never been acknowledged?
Oh no.
Okay.
Remember, we are talking about reliable delivery. TCP is about reliable delivery. Yes, it is reliable delivery. So you will keep retransmitting. When the timer times out, you will retransmit. Unless the server has crashed. Finally, it will definitely acknowledge. Even if it acknowledges as a group, it will have to acknowledge. And also remember that if something is out of order like it is here, it will never be passed to the application. So until it is sure that this has been received and it has been acknowledged, you should also not slide this window. So you can also not slide your window until you are sure that it has been received. So basically, if it doesn't happen, then I guess the transmission will come to a halt. It will not move forward. I'm not sure why you asked that question, because the anticipation is that this channel is working and that whatever is sent is being received. So ultimately the acknowledgement will come, maybe after several retransmissions, but it's expected to come. Even if there's congestion, we already said that when there's congestion, there are control techniques that try to remove the congestion so that communication can move forward. Otherwise, it will not move forward. Right. So I guess that's okay. Let me talk about flow control. Now notice I have talked about flow control separate. I'm talking about flow control separate from the error control. In the sliding window that you have looked at previously, the two are combined. The two are combined. So for example, in the stop and wait, if you send one, you receive an acknowledgement, then it means you can continue. So the flow is controlled automatically. Don't send me another one until you receive what? An acknowledgement. So once it receives an acknowledgement, you are free to send again. And when you receive before you receive an acknowledgement, you can't send. So the flow is controlled automatically by receiving the acknowledgement. That is in the stop and wait. What about the window? Let's assume you have a send window and you have a receive window. How is the flow controlled? So assume you sent from 0 to 4 and you're waiting for an acknowledgement. So you sent, this side sent frame number 0, frame number 1, 2, 3, 4, and then it stopped to wait for an acknowledgement. Now, if this side acknowledges, frame number 0, then it means we can slide the window and we can send one more. So now we will be at 5. Okay? So by receiving this acknowledgement, you have the freedom to send another one. In other words, you have the freedom to send another one. But before you receive an acknowledgement, you cannot transmit again. So let's assume the acknowledgements for 1, 2, and 3, and 4 get lost. Then this side has no right to send some more because it has sent all that is in its send window and it has not received an acknowledgement. So it will just wait. If perchance these ones got lost and it got the final one, so assume they were being sent one by one, it's only that they got lost. So the final one for 5 actually makes its way. It will stand in for all the acknowledgements that have gotten lost. And it's only when the acknowledgement for number 5 comes in that now the sender is free to send again. And now it can send from number 6, if it's sending 5, 4 at a time, it can send from number 6, 7, 8, and 9, because it's allowed to send several before stopping and waiting for the acknowledgement. So what am I trying to say? In the normal sliding window that you know about, acknowledgements mean you can send some more. If you get no acknowledgement, you have no right to send. So it automatically acknowledgements control the flow of data from sender to receiver. Now, as I have said, in the transport layer, it doesn't mean the same. It does not mean the same because, as we said, the client must pull the data. So just by receiving an acknowledgement, as we have seen in the error control phase, does not mean you have the right to send someone. So the flow control problem is the same as in the data link layer. Basically, you want to control how much the sender can send. However, the transport layer flow control mechanism is a little bit more complex. And the complexity is brought about by the differences in the operating environment, which I think I already tried to explain, that there were differences in the operating environment. I think I went through all these things And as I said, they are not supposed to be in this set of notes. I think by mistake they are there. So I've skipped them. So basically, flow control will ensure that the sender does not overwhelm the receiver. And the receiver will send some feedback to the sender to let the sender know about its current condition. In other words, should it send some more? Okay, in the normal sliding window, when a receiver sends an acknowledgement, it's basically saying you can send some more, because by that time it has passed data to the upper layer. So there's one more free buffer. But in the transport layer, we said that is not the case. Data may still be sitting in the buffer. It has not been pulled by the client. So if I send you an acknowledgement, it doesn't mean I have a free buffer. That's not what it means. It just means I'm acknowledging that I've received it. But if we have to control the flow in the transport layer, then we have to get some kind of feedback from the receiver to tell the transport layer on the sending side when it can send. But now, this diagram basically tries to show the feedback. I haven't told you the details of the feedback, but let's look at how that feedback mechanism works. Let me try. I hope I can explain it with this diagram. Notice that there's a producer and there's a consumer of the data. So this one, of course, is producing data to be consumed by this one, right? That's why they are communicating, right? But as we say, this producer here must pass data to the transport layer. So the transport layer is now consuming this data from the application. We can say in that sense, this one is the producer and then this one is the consumer. How is it the consumer? Because it has some buffer where that data is going to be stored. Then once the data is stored in the buffer, then the transport layer obviously must package that data. As we said, it must put a header around it and then send it to the other side. Okay. Now, when it sends it to the other side, obviously, then this becomes the producer and then this one the consumer. And as we said, it is stored in a buffer waiting to be received. Then, of course, we said it must be processed in such a way that when the consumer asks for it or when this side asks for it, then this side then becomes the producer and this one becomes the consumer. So how then does flow control happen in that sense? The flow control happens in the sense that, as I said, if this consumer never requests to consume data, then the buffer of the producer will fill up. It will keep filling up because remember, data is coming in from this other side. Data is coming in from this side. So if this consumer is not consuming, then the data is filling up. Okay? And when the data is filling up, then it means that this side, which is the consumer of the data coming in, must now talk to this producer to say, look, don't send me any more data because it is not being consumed by the rightful application. So it has to kind of send data back to this producer here to tell it, look, I don't want you to produce any more data and send it to me. Okay? So it's happening because this one is not consuming. Okay? So we have to find the source of the data that it's consuming, where it's coming from, who is producing that data. And we have to tell this side to stop producing more data. But remember that this side is also getting data from this producer here. So it means that if messages are coming from the other side saying, please don't produce some more, then this side also has to identify who is producing the data that I'm consuming here. It's coming from this producer. So it must tell this producer, please stop giving me more data. So that's how flow control happens. It starts from the receiver. The receiver feeling overwhelmed, and finding who is the source of the data that is receiving that's causing its buffers to be full, and telling that producer not to send any more data or not to produce any more data. And notice that it can go all the way back to the sending application. Remember, you must distinguish between the transport layer and the application. So if things don't go too well, then it will, the warning will go all the way back to the application that is producing all this data, that is making the receiver not be able to consume. Okay? Okay, so that should give you an idea of what happens. So I've already explained about the buffers. It actually comes from the idea that the buffers on the receiving side are becoming full because the receiving application is not consuming the data. So the transport layer eventually also cannot receive more data, must talk to the sending side transport layer. And the sending transport layer, because it's receiving data from the application, must also now tell the application, please don't send me any more data. But remember, flow control is two-way because the TCP connection is a two-way connection. I've only described it using a one-way, but it could also be going the other side. Now, if we don't do flow control, remember that packets will get dropped on the receiver side. So the receiver, in order not to drop packets, wants to stop the dropping of packets, must initiate the flow control. Now, so how does the sending side initiate? Because flow control is actually initiated at the transport layer. It is initiated at the transport layer. So what does the transport layer do? Now, to control the amount of data that can be sent, the receiver will have to advertise its receive window. So how does this side tell the receiver to stop sending more data? It tells it how much window space it has. Okay, it tells it how much window space it has. So let me just create a scenario here. Assume that this side, this sender side, this transport layer sender side, since it's using a sliding window, let's assume it was allowed to send maybe 600 bytes. So the receive window, the send window is 600 bytes. Now, when it sends 600 bytes, let's assume it sends 400 bytes in batches of 200. So each frame has 200 bytes, 200 bytes. So it sends 400 bytes. And it receives an acknowledgement saying, I have received the 400 bytes. Okay? Now, naturally, if we were using the normal sliding window, it could slide its window from 0 to 600, and now it could then send from 401, it could send another 600 if it wanted, if we were using the normal sliding window. But as I've said, on this side, maybe what could have happened is that the 400 bytes are still sitting here because this consumer is not consuming them. So in order to prevent this side from sending another 600 bytes, or at least 400, it must send back an acknowledgement and say, look, I have acknowledged having received 400 bytes, but you are only limited now to sending me 200 bytes. So this is what we are calling the receive window. So in the transport header, if you go back and look at it, I don't have the diagram here, I would have looked at it, but I think you need to look at the transport header. there is a section called the receive window where there's a sequence number. I think there's a sequence number, there's acknowledgement, and there's also a receive window. So in the transport layer header, there are three very important values: sequence number, acknowledgement number, and receive window. So when the receiver is acknowledging, there is the acknowledgement for saying how many bytes I have received and which one am I now expecting. So assume that's the acknowledgement. I'm now expecting from 401. But it will also say I'm expecting from 401, but my receive window is currently 200, which means you can only send from 401 to 600. So that this side does not slide its window automatically, assuming that the initial 600 bytes it had as a window is still open. It will be told with each acknowledgement that comes how much buffer space it is having, and therefore how much more it can still send. So that's how the transport layer flow control works. So notice, to control the amount of data that can be sent, the receiver will advertise its receive window. And this receive window is the maximum data that can be accommodated in the receive buffer, or the spare room that is still available in the receive buffer. Notice that on the sending side, TCP stores the data needs to send in the send buffer. The receiver needs to send an acknowledgement to the sender for every packet. But with the acknowledgement message, it also sends another value. As I've said, it also sends another value of what is currently available. So there's acknowledgement and there's the receive window. Or there's the, there is the receive window. So the sender, on receiving the acknowledgement, it will know how much data has been received and how many more bytes it can send, without waiting for an acknowledgement, that is, without waiting for an acknowledgement. So in the example I have given here, if it receives an acknowledgement of 401 with a window size of 200, it means it can send another 200 without waiting for an acknowledgement. So that's the general principle of flow control. I think maybe the best thing is just to show it. Okay, I think I explained this a little bit earlier when I was saying the buffer can fill up if the user is not pulling the data. Or, yeah, it's not pulling the data and the receiving transport itself cannot keep up with the flow of segments from the sender. So there are two things that cause the buffer on the receiving side to fill up. The user is not pulling the data and the sender keeps sending more. So at that time, the buffer will fill up and data will begin to be dropped. And so we'll need we will need to slow down the sender. Now, this flow control can be controlled in many ways. But the one I'm using, the one I'm explaining to you that is adopted at the transport layer is this one I'm calling the credit scheme. I think it goes by many names, but the reason why it's being called here a credit scheme is like giving the sender a credit, like telling it, look, I've received bytes up to 400, but I'm now giving you a credit for 200 more bytes, so that you can only send me 200. So with every acknowledgement, it's like it's given a credit of how much more it can send. So there are various ways it can respond to the flow overflow, the overflow issue. One, it can do nothing. It can refuse to accept further segments. It can trigger, it can use the fixed sliding window protocol, which we've said won't work anyway. But the one that normally works is this credit scheme, which I think I've explained. And I don't know if I need to explain it more. Let me use an example. Now, maybe there's something I need to say, which I haven't said. You can see here, I'm saying that basically said that the receiver will change the window size every time it receives data, the window size changes. And then it sends, upon receipt of data, it sends the window size. It sends the window size back to the client. And then the sender must adjust itself. So initially, if it thought it had 600 bytes, now it must adjust. I had 600 at the beginning, but now I've been told I have 200. So it keeps adjusting its window size based on what the receiver is telling it. So notice that in this particular method we are talking about, acknowledgements and flow control are two different things. Unlike in the other case where we said acknowledgement is also the means of flow control, here they are decoupled. Flow control and error control are decoupled. They are not the same. Now, and another thing I need to say, because now the next thing is an example, another thing I need to say, this adjustment does not always mean that the window size becomes smaller all the time. The window size can also grow. So for example, in the example I've just given you, I hope the diagram is still there. So now, assume the receiver has been told, look, I'm expecting you to send me from 401, but you can only send 200. So it sends the next from 401 to 600. Assume it sends that. But let's assume that this client pulls the first two messages and therefore removes from the buffer 400 bytes. Let's assume it does that. Now, when this new message arrives, which is from 401 to 600, obviously it will be placed in the buffer. Obviously it will be placed in the buffer, and now it will come first there. Because the other two have been removed, it will be the first in the queue. Now, how much space does this side have? Now it has 400. So when it acknowledges this one, it will say, look, the next message I'm expecting from you should start from 801, because the other one was 200. But now the window size is 400, right? So now the window size has adjusted upwards. Why has it adjusted upwards? Because the client program pulled the 400 bytes into the application. So the size of the window keeps changing based on the dynamics of the system. It can go down, it can go up. So with every acknowledgement, you may have a different window size depending on what's happening on the receiver side. Now, another thing I need to say, let's assume that when it is now receiving this acknowledgement or receive window acknowledgement, it is now told, assume it has been told now you can send 400, and it actually sends 400. And when it sends this 400, let's assume what happens. The client doesn't pull. So the 400 have now been entered into the buffer. Now, when it acknowledges the two messages that have just come in and filled this buffer, remember it will indicate a receive window of 0. If its buffer can only accommodate a maximum of 600, the receive window will now be 0. So it will be told, I have received up to now, this was 801, 1001, and 1201. You receive an acknowledgement that says, I have received up to 1200, and now I'm expecting 1201, but I have no more space. So the receive window has now reduced to 0. And it will say, look, just know I have received, but you can't send anymore because I have no more buffer space. And at that point, the transport layer will just have to stop sending any more messages. And that's why I said, once the receive window has become 0, then now the transport layer, if its buffers are full, it now must stop this application. Remember, it can't send anymore because the window size is 0. But if this application continues to send it data, it has no more buffer space. Assume the buffer space of this one is also full. Now it must go back up to the application and say, look, you can't give me any more data because I've been stopped from sending any more data. Now, what will happen? Let's just assume that this is what happens. The application now decides it wants to pull this data. So it pulls maybe the first one. So now we have 200 bytes available. So this side will send an acknowledgement. Remember, it had sent an acknowledgement 1201, but received Windows 0. It will send an acknowledgement now, look, I have received up to 1201, but now I have a window size of 200. So it will just send it once the buffer is freed, it will send this acknowledgement again. And then now this side can begin to send. Remember, it was stopped from sending, but now it's being told, look, you can send some more, but you can only send 200. So now this side will send now from 1201 to 1400. And if the client doesn't pull anymore, it will be sent back an acknowledgement 1401, but window size 0 again. So this window size that is controlling the flow is fluctuating. On the receiver side, it's fluctuating based on how the client is behaving. It can go to 0, it can rise, it can go down again, and so on and so forth. But now we face one problem. I can see I'm at 1 o'clock. But let me just say this in conclusion. It can so happen that the receiver sent a window size of 0 to the client side, to the sender side. And then when the window opens up again, or when the buffer space opens up again, it sends another message telling the sender that I have now more buffer space. But maybe that message may get lost. So now we have a deadlock. Because the sender thinks they have told, the receiver thinks they have told the sender that there is more space and you can now continue. I stopped you, but now I'm telling you I have more space, so send more data. But that acknowledgement may never arrive on the sender side. The receiver is waiting, the client is waiting to be told if there's more space. So now we have a deadlock. And if we don't have a mechanism to unlock that deadlock, then communication will just grind to a halt. But obviously somebody has thought about it. So what happens? So what happens, I think, is it's somewhere after those examples. I wanted us to go through at least one example. But this is the deadlock mechanism I'm talking about. That the window size may go to 0. As you can see, the acknowledgement has been given there, but the window size is 0. And then subsequent segments to unlock the sender gets lost, and so now there's a deadlock. But obviously, there has to be a way to sort it out. So what normally happens, and I'm looking at the last set of bullets. So when the TCP receives a 0 window size message, that is when the sender receives a message that tells it the window size is 0, so you cannot send anymore. it starts a timer, and that timer is called a persist timer. So when the timer expires, it will send some kind of message to the receiver, to kind of probing it to find out, has anything changed? Has your window size changed? And when the receiver receives this probe, it should send that acknowledgement we talked about, reminding the client how many bytes it has received and what is the window size. So that probe gives the receiver a chance to advertise its window size again. So in the case where there was a deadlock because the advertisement of the window got lost, if this timer goes off and the sender probes the receiver, then the receiver will send it again. So it will unlock the deadlock. I hope you see that. So a window size of 0 was sent. More buffer became available. So the window size increased and a message was sent, but it got lost. So now this side is waiting, this side is waiting. How do we unlock that? We say that usually when the sender side receives this message that tells it the window size is 0, it starts a timer, a persist timer. When the timer expires, it probes this side and say, look, I have waited for too long to be told whether I can continue sending. Is your window size okay? Then this side is bound to send a message. So even if this one got lost, this one will unlock the deadlock. This one will unlock the deadlock. But even if this one got lost again, remember every time it sends, it sets a timer. So it will send another probe. So this timer, it will be set again and again until it gets some kind of acknowledgement telling it what the current window size is. So even if the probe gets lost or the reply of the probe gets lost, another probe will be sent until it gets to know. But remember, if it sends a probe and the window size is still 0, this message will still say, look, I told you to wait, my window size is still 0. And so it can keep probing, and if the window size is still 0, it will be told it is 0. But maybe at some point it will probe and it will get a response telling it the window size has gone up. I hope I'm communicating.
Yes.
You're following?
Yeah.
I hope I haven't lost you. Now, I want you to look at this diagram. I just want you to look at this diagram briefly. It's a very quick diagram here. So let me just, I think from what I've explained, it should be self-explanatory, but let me just use this in conclusion. Please just give me 4 minutes. I think by 10 past you'll be through. So look at this diagram. Notice here that this message is a 2K message with sequence number 0. Notice the buffer is currently empty. So this message arrives and it is put in the buffer. So 2K of messages in the buffer and an acknowledgement is sent. What is the acknowledgement saying? The acknowledgement is saying that the next message I expect is 2K plus 1. In fact, this is using just 2K. So it's acknowledging the actual number of bytes. But remember that this is 2K, yeah? So 2048. But the window size is also, it has an extra 2K. So this buffer here is 4K. So it has an extra 2K. So notice that the receive window is 2K. Okay? So when this arrives, this side knows it can still send another 2K. So it sends a message 2K, but the sequence number now is 2048. Okay? So it sends it, and now the buffer is full. Notice that now the receive window is 0, but it has acknowledged that it has received 4K bytes. But now the window size is 0. So the sender is blocked. The idea here is that the sender is blocked, the flow control has now taken effect, and the sender is being told, please don't send anymore because my buffers are full. Then notice the application reads 2K from the buffer, and now there is 2K space in the buffer. So the receiver sends this new message which says, look, I have received up to 4096 bytes, but now I have free space. I have 2K free space. So it sends it to the client. So now the client has been given permission to continue sending, but only up to 2K of information. So now it sends the next message, but it chooses to send 1K. I don't know why. It has permission to send 2K, but it chooses to send 1K with sequence number 4096. So when that 1K arrives, remember we still have 1K more in the buffer. So obviously the acknowledgement here will say, I have received up to 4096 plus 1K, whatever that is, and a window size of 1K. I hope that makes sense. And I think we will stop there, unless you have a question. So please read the notes. I think I have tried to explain without going through the notes, but please try and read. If you have understood what I've said, the notes will make sense. If anything doesn't make sense, please let's discuss it at the next class. Is that okay? Is that okay?
Yes, ma'am.
Yes.
Okay. Thank you very much and have a good day.